My name is Mark Ritz. I'm the Commercial Business Unit Manager for Rheem. Excited to be here. Looking forward to talking about maintaining temperature and humidity in critical zones. We all have different definitions of critical zones. Some are more critical than others. Typical scenario: one HVAC system, one thermostat, multiple zones, a fixed outside air intake. It's surprising how much the codes are changing where we're going to more economized or more CO2 sensors. But at the end of the day, it comes down to dollars in a lot of applications, and they'll put on the cheapest method to meet code. So when we start thinking about humidity and controlling temperature, the outside air is not on our side. So we end up with fixed outdoor air intake. In our industry, the maintenance is top-notch, first class. Everybody's running their service agreements, doing maintenance. Kidding. Once those units get on the roof, again, I'm brushing with a broad stroke. Many of your clients have impeccable maintenance agreements, but when I think about the typical DX type equipment, and that's probably what we're talking about is DX equipment, particularly rooftop units, low rise. Once those things hit the roof, they're out of sight, out of mind until something happens to them. So the maintenance is not top of mind in a lot of cases. So talk about the main variables. Temperatures. Humidity, dry or damp. And when we talk about particulates, we're talking about dust, grease, oil, pollen, hair, just everything that's in is in a building. This is a very relative slide in meaning that it's accurate, but we know how temperature and humidity affect our feelings. Now, if you're in South Florida, 60-70% humidity is probably about right. You're accustomed to it. I'm from Oklahoma. I like mine about 40. For those out in the West, you'll be dying at 40% humidity. You have none. So a little bit of this is relative, but we think about critical zones and controlling humidity. We think about how it affects the overall comfort of the space, and that zone, that range, 40 to 60% is that sweet spot. That's where the temperature, the actual temperature, and how a person or an occupant feels is one and one. We start getting above that, obviously that temperature starts creeping. You start feeling warmer than what the actual room is. You get below that, then you start getting cold and clammy. So that's where we want to find that sweet spot of that 40 to 60%. Take it back to basics a little bit. Take the human body. Same thing works when we're talking about a building. Evaporation requires energy. So evaporation is our cooling process. When we sweat, we evaporate. Or when we sweat is our cooling mechanism, and that evaporation is what is the cooling mechanism. When it's hot and humid, the sweat doesn't evaporate, so we feel much warmer, and we don't have that cooling mechanism. So ideally, whether we don't even have to be sweating, but be sitting in an internal environment such as this, and you're still fighting that cooling mechanism of not being able to cool off from a personal aspect. So we have limited evaporation in humid conditions. It makes for an uncomfortable environment. We hold in some of that humidity. When it's colder outside, we like that little bit more humidity that holds that temperature in. So therefore, the humidity does quite apply for cold and humid. So why the cold, damp zone? Well, if we think about what we've done over the past 30 years from a cooling standpoint, obviously the fresh air requirements that are required, we're fighting against outdoor conditions. We've had to oversize the equipment in order to oversize the coil side, get more latent capacity to bring up the efficiency levels. We've grown from an efficiency standpoint. 2010, we had an increase 20%, had another one in 13, and we'll have a third one in 2018, and on 2023 has already been identified for higher efficiencies. To get there, you get larger coils, you get more latent capacity, which leads us to an overcooled or damp air component. So we're fighting against that side of it too. We're fighting the overcooling. We're fighting as we start closing up the buildings. Well, that'll get into more of the particulates in just a moment. But so how do we, and all this is stemming, I'm leading up to the issues, the challenges that we're faced with getting to a solution with emerging technologies. But today we're taking hot, humid air, putting it through an oversized cooling coil. We're dropping it down to condensing, and we're pumping it into the space, which at 55, 56 degrees is running about 90% to 95% relative humidity that's going into that space. How do we get around? That's where we're headed, is how we overcome that. So not to make an eye chart, and I was told not to get too close to that speaker, so I'm trying to hold my spot up here just a little bit. But to put it in a psychometric chart, you think your mixed air, you got 75% return air, 25% outside air, 80, 67 return, 95, 78 outdoor. And you drive that down, fall it down, you got a cool temperature of 52, 55 degrees with a 52 degree wet bulb. You're in that 95% relative humidity area that's coming out of coil. Again, we're looking at ways to overcome that. There's a component that comes at, not only from a comfort level, but from a particulates areas, that optimal zone for bacteria, viruses, fungi, and mites. And that also plays a factor when we talk about humidity. The more moisture in the air, the more those particulates hang onto that air and carry through the system. As we pull moisture out, there's not as much to hang on to. Therefore, it's easier for it to filter through your filtration system. And again, they found that optimal zone from bacteria, viruses, fungi, and so forth in that 40 to 60% range to be that sweet spot. Same information, just from a different source. That optimal zone conditions is in that 40 to 60. One of the things I'd like to point out is when we're talking about filtration, because again, we're looking for that optimal temperature, humidity, and particulates for that critical zone, which again, that critical zone is us sitting in this room, your customers, your clientele, that office, that restaurant, and so forth, that when you carry out your pleated filters, pick up about 40% efficient. So the more we can help that air passing through, and again, broad brush here. I know everybody's dealing with applications. We're using HEPA and electronic. Obviously, those are the high end. Those are the one spectrum of it. But you've got applications out there that after the first year, after it's commissioned, and filters may never get changed, or they go back in with a simple hog hair. You're lucky to get a 2-inch or a 4-inch pleated in there. So now you're down about 40% efficiency on picking up the particulates. And again, you're not even touching the viruses or the smoke. You're really just picking up little bit of hair, a little bit of dust, and so forth, that you're up around 10 microns is what you're picking up. So anything we can do to assist that in that air side is nothing but a plus. Controlling humidity. The impact of standard design. Creates high humidity issues, removes minimal moisture from the air. Overcooling causes a cold, wet zone. Undercooling causes a hot, wet, or a hot, humid zone. So that's what we're dealing with. That's your typical standard unit today. Of course, the cooling component is removing moisture. In order to do that, we're overcooling the space. We're driving that temperature down, so we get cold, clammy. Again, we're in a situation where we're not. It's not a comfortable situation for our clients. This has been solved. We're doing it today. We've been doing it for years. It goes all the way back to, 20 years ago, when you just stuck a strip heater in a duct, and you ran both the cooling and the heating at the same time. Not very efficient. You're running cooling and heating. Then we've gone to reheat coils. Standard put a reheat coil downstream of the evap coil. Still works, but you still run you still have the opportunity to overheat and overcool because of the control side. Your standard dehumidification units, in a lot of cases, are on-off. You're either in reheat mode, dehumidification mode, or you're in cooling mode. And it doesn't satisfy until it doesn't shut off till you satisfy. The other piece of it is that a lot of your current technologies are not efficient because you're measuring two different variables. So, other than the fact that you do have the capability of raising your temperature or raising your set point temperature if you get the humidity right, doesn't always coincide with the comfort level. So with measuring two variables, you cover cooling, but you haven't satisfied humidity, so you have longer run times. So what we'll get into is areas where we may even be able to, technologies you can stay out of reheat mode. But reheat coil completely solve the humidity problem. Not exactly, yes, in some cases, but there's better ways of doing it. So what is happening when we are reheating? Using reheat to reduce humidity. You got the same hot, very humid air coming in, 80 degrees. You're overcooling it, pulling the moisture out, and we're reheating it. Again, the idea is how do we control that second temperature to get neutral air? Because we're looking for that cool, comfortable air. 58, 60 degrees, about between 40 and 60% relative humidity, depending on your set point. Again, that's a relative term right there, because in Oklahoma we're not near as humid as Florida, and I like that about that 40. It's that what you're accustomed to. So how do we create a predictable indoor environment? Typical reheat provides a more comfortable light, yes. It does overcool the zone when there is no latent heat in the zone. It can still lead to cold spots or cold, damp zones. And this is where we talk about the provide neutral temperature. When we talk about neutral air, able to bring outside air and return air, which is a mixed temperature properties, to a neutral temperature. And we talk about the neutral temperature is one where the dry bulb and wet bulb leaving the space, leaving through the registers, is equal to or similar to what's being returned in the zone. So again, creating neutral air, hot air coming in through the return and your outside air, overcooling, pulling that moisture out. Again, bring it to that dew point as low as possible, get as much moisture out of it. Again, bringing up your efficiencies, running it through a reheat coil for comfortable air that hits the space. I always use the analysis, and it's a Florida analogy, but you hit certain casual dining restaurants, chains where they're just using straight cooling in Florida in July. You're taking a sweater with you, or your spouse is, or because the only way to keep it from being warm and clammy, they're driving that temperature down. Still a bit clammy, but it's going to be cold in there at 6 in the evening for dinner. Again, that's an uncomfortable situation that's not providing predictable air, because again, everything that we do from a temperature to the particulates, dehumidification is the biggest variable, because you have different entering conditions, you have different load in the buildings, and so trying to find that control or that technology that will address those variables is the key. So if you recall the previous slide, we were about 95% relative humidity at 52 degrees. With reheat, you follow that arrow out, you still got a return, a 68 or a 78 or 80, 67 return. You still got about a 95, 78 mixed air, which gives you a warm return air coming through. You still have your same cool temperature. That doesn't change. We still have that heavy evap coil, that large evap coil. We're still drawing that moisture out. But what we're looking to do is with the reheat coil, you're pulling that, you're adding heat, which again lowers that humidity so that you can get to neutral air, 68 degrees, 52% relative humidity in this example. So what is the emerging technologies? Variable frequency drives, 2-speed blowers, fan control. It allows for more accurate temperature and humidity control. Example I like to use hypothetically. We take this building right here, or take this section, and again, I live in the DX world, so I use something to the analogy of a 10-ton unit designed for full, 100 people in here, kind of like it is right now. But you guys design and commission for full load, but it may only see that full load at maximum temperature, outdoor ambient temperature, maximum load, a small portion of the time. So when a space similar to this is working off of partial load, use 10-ton as an example. 2 5-ton circuits, two stage. You could be running 5 tons of cooling, but you're still pulling nominal 4,000 CFM through it. You're getting very little latent capacity. You're pulling very little moisture off. So again, in order to overcome that, you're driving that temperature down to try to get as much of that out, which is it's hard to overcome because your airflow is not matching your capacity. By using multiple speed blowers, and the technology just continues to expand. Obviously, variable frequency drive has been around for years, but as we start seeing it be carried into additional units across our industry, it starts bringing that cost point down, makes it more economical. The return on investment gets better. But now we get to start matching that airflow to the capacity, which in turn can keep us out of reheat mode. We can start doing measuring that variable and predicting what that's going to look like. It allows more moisture to be pulled from the air, and it also prevents overcooling the space. The other piece to that is, it's not in here, but one of the other keys to that variable frequency drive or multi-speed blowers is the ability to, is the cost savings. Because you run that blower at a lower speed, and so there's a watt savings that comes along with that. So when we start thinking about dehumidification, there's a couple different ways. We talk about the reheat side of it, but if we look at the functionality of a dehumidification mode, we start thinking about multi-stage dehumidification to be able to dial into the exact temperature and humidity you're looking for. That's where we're at today. Example, two-stage equipment with multiple stage dehumidification components. Meaning, in this scenario, we can operate in first stage cooling, we can operate in second stage cooling if need be. And when you think of first stage cooling, you're running low speed fan because you're utilizing that VFD drive. So you're doing more latent capacity that way. We're measuring two different variables, temperature and humidity. So if you satisfy the temperature component, but you still have a humidity call, you bring on first stage of dehumidification, which is a single stage operation, and you bring on your reheat coil. That allows you for you're only slightly off, so now you get to adjust your. You're not overcooling, not overheating. You're dialing it in where it needs to be based on your humidity. In this scenario, you're also modulating the outdoor fans, so you get the right coil temperature on the reheat coil. Previous reheats was either on or off. You fired it up and you ran that hot gas through that reheat coil, and you got what you got. Today, with modulating outdoor fans, as you recall, you're using the heat off that condenser coil to warm up that reheat coil. So by modulating the temperature, you can ensure a predictable and measurable coil, which in turn that's what gets you to a neutral air, regardless of the internal or the incoming conditions. Again, we could be dealing with heavy load, heavy latent capacity. You could be dealing with a unit that that's been shut off for a period of time, like the fire alarm goes off, and I don't know when they'll ever get it kicked back on. Or if you do a setback at night and you're coming back on in the morning. Any number of variables from a sensible load to a latent load, you need to be able to control that to match the spectrum of incoming conditions. Again, as I talk about first stage, you have a first stage of cooling. You have a first stage of dehumidification. When you're using two-stage equipment, and you're varying the fan speeds, you also have a third stage of dehumidification available. You can bring on two stages of cooling and leave the reheat coil in operation. Say your set point, you're not getting enough moisture pulled off of the coil. You're not satisfying. Now you have the capabilities of adding more capacity, at the same time still delivering somewhat neutral air with a little bit of sensible in it. Again, the technologies of variable frequency drive to minimize the dehumidification, dehumidification mode, the ability to stage it, ability to modulate it and maintain a true coil temperature is the technology that we're talking about here. Just for a recap, now that I've talked about all that, I'm just going to touch on the system itself and just make sure we're all understand that the technology itself. Typical system, starting at the compressor. High temperature vapor goes to the condenser coil. Heat's going to dissipate in the atmosphere off that coil. With liquid line back to the TXV valve. We're going to have a coil temperature of 55, 58 degrees, anywhere 52 to 58, pick the number. We're going to take that moisture off. All that moisture is going to drop. In a typical system, this would go straight to the discharge. So that's where we get that 52, 55 degree, 95% humidity hitting that spot. So when you have a call for dehumidification, your temperature satisfied, but the humidity, that second variable, you have the capabilities of opening a discharge solenoid valve, closing a liquid line valve, and open your reheat valve. And now we're taking that heat, it's called two-phase, taking that hot gas and liquid mixture, and we run it through that reheat coil. Reheat coil is set at a given temperature, and again, it's modulated or it's measured by your. It's a set, and we can maintain that temperature based off of those fans. The valves are set; they're going to open or close, but by modulating those fans, we can ensure that coil maintains its designed condition to give us neutral air.